right, today we are covering areas of regular polygons. So we are going to start out by reviewing what a regular polygon is. When you see regular in front of polygon, this means the polygon has all sides congruent and all angles congruent. So the picture that you see off to the side is a regular pentagon, and we would say that it is inscribed in circle A. We could also say the circle is circumscribed around the pentagon. And we know that circles have a center and a radius, but in this section, because the regular pentagon we are thinking of as being inscribed in the circle, the center of the circle is also the center of the pentagon, and the radius of the circle is also the radius of the pentagon. So we will be referring to the radius of a regular polygon in this unit, and to understand again that radius is the radius of the circle that's circumscribed about the regular polygon, but then we do consider the radius of that polygon. Notice that a radius does go from the center to a vertex of the polygon. Then a new term called the apothem. The apothem of the pentagon is the perpendicular distance between the center and a side of the pentagon. So this is drawn in, actually let me go back and highlight here too. So I'm going to highlight the radius. This would be the radius of the circle and the pentagon. And then the apothem is always from the center perpendicular to one side. So this would be the apothem of the pentagon. And the apothem does, it bisects this angle here. So if you draw in two radii, you end up with an isosceles triangle here because these two radii would be the same length. And then this altitude that you're drawing in for that triangle does bisect this angle, which, as we're going to see, is called a central angle of a polygon. So for any regular polygon, the central angle is an angle whose vertex is the center, and the sides contain two consecutive vertices of the polygon. So again, this entire angle here would be the central angle. So the apothem divides it in half. But to find the measure of a central angle of a regular polygon, so n is representing the number of sides, we're going to fill that in. So to find the measure of the central angle, you take 360 and divide by n, which is the number of sides. Okay, so in the first set of examples for each of those regular polygons, we're going to sketch in a radius and an apothem, and then we're going to find the measure of the central angle. So I'm going to start with A, the square that we have here. I'm going to just put a point where the center would be. So to draw a radius, you're drawing from the center to any vertex. I'm just going to draw it to here. So this would be a radius. And then the apothem would be from the center perpendicular to a side. So I'll draw it down like this and label my 90-degree angle. We are going to be labeling or calling the apothem A, little a, once we get to a formula. So if you wanted to label that A, you could. So that's the radius and the apothem. Then the measure of the central angle. So if I drew in another radius, remember then it's the angle with a vertex at the center, and it's basically between two radii is what the central angle is. So I'm finding the measure of that angle, and that is the 360 divided by n, so it would be 360 divided by a square has 4 sides. So the central angle for a square is 90 degrees. Okay, we'll do the next one also. This has 8 sides, so we have an octagon. So if I draw in the center, from the center to a vertex is my radius. From the center perpendicular to a side is the apothem. And then I'm going to draw in another radius just so I can see where my central angle is, and I'll just find the central angle down here. So since an octagon has 8 sides, I would take 360 divided by 8, and that would get me a central angle of 45 degrees. Okay, so why don't you go ahead and fill in or draw in a radius and apothem for the triangle and the hexagon that you see, and find the central angle for both, and then you can check them. Okay, feel free to pause the video if you aren't quite finished, so you can finish up before you check, but I'll show the last two. So you have your radius, apothem, central angle is 120 for every regular triangle, which would also be called an equilateral triangle. And then for the hexagon, radius, apothem, central angle is 60 degrees. So here's how this all ties in to finding the area of a regular polygon. So we have this formula here, capital A equals 1/2 times little a times capital P. Capital A is standing for the area of the regular polygon. Little a is the apothem, and that would be the length of the apothem. And then capital P is referencing the perimeter of the polygon. So what I'm going to ask you for when I give you a regular polygon, this is what I want you to find. I want you to find the measure of the central angle, the radius, the apothem, the perimeter, and then the area. And to find the area, you are using the apothem and the perimeter anyway. Sometimes you are given some of these pieces of information. You just have to find that from the shape that you are given. So for example 2, we have a hexagon. We have 6 sides. So actually we just found the measure of that central angle up here. That would be 60 degrees. But if you want to write here, just remind yourself how we got that. It's 360 divided by our number of sides, which is 6. So the central angle is 60. And again, that would be this full angle right here. So what that means, and now how we're going to use this, is this apothem that's drawn in, again, is bisecting that angle. So each of these is 30. And that means if I were to take out one of these right triangles, because you're creating 2 right triangles, so if I were to take out one, I'm just going to draw it below here. So this is a 30-degree angle, meaning this is a 60-degree angle. I have a 30, 60, 90 triangle. So in this section, we are reviewing special right triangles. We will also review SOHCAHTOA if we need it. So off to the side here, I'm just going to remind you of the formulas for a 30, 60, 90 right triangle. So the leg that is opposite the 30-degree angle is the short leg. I'm going to call that X. So short leg. Then the other two sides of the triangle are in terms of X. So the long leg opposite the 60 is the short leg, so X multiplied by the square root of 3. And then the hypotenuse is always 2 times the short leg, so 2X. Okay, so if you look back at this small right triangle we have here, the hypotenuse of each of those 30, 60, 90 triangles, that hypotenuse is the radius. And because I know that this full side length of my hexagon is 3, this apothem again divides this in half. So this short leg is 1.5, so that would be in place of my X, meaning my hypotenuse is twice as long as that. So 2 times 1.5 is 3, meaning my radius is 3. So radius I know is 3 meters. Then my apothem is the long leg of that right triangle, and the long leg is the short leg multiplied by the square root of 3, so that would be 1.5 multiplied by the square root of 3. And I'm actually just going to leave it like that. I'm not going to type that in my calculator and round it, and that's in meters also. I am just going to leave it as exact. And then the perimeter of the polygon, so since I know one side length is 3 and I have a regular polygon, all 6 sides are the same. So the perimeter would be 3 multiplied by the 6 sides, so 18. And that's also measured in meters. And then lastly, my area, which I'm using this formula, so it's 1/2 times the apothem times the perimeter, or you can do apothem times perimeter divided by 2. So I would have, I'm actually going to do this divided by 2. So I would do 1.5 square root 3 multiplied by 18 divided by 2. And this you can round for your final answer. So if I type this in, 1.5 times the square root of 3, I'll hit enter, times 18, enter, divided by 2, enter, and I get 23.4 approximately. So the area is approximately 23.4, and that would be in meters squared. So there takes a little bit of problem solving in these problems because you have to take what you're given, which you're going to see with the next two. We're given, perhaps different pieces of information, but you have to take what you're given and then use maybe past formulas that we've learned, like 30, 60, 90 triangles, and apply that to find what you need. Okay, so we're going to go on to example 3. We are going to do all of these together because they're all a little bit different, so I'll lead you through them. So 3, we have a square, and again, we're finding the same information. So measure of a central angle, we did find the measure of a central angle of a square on the front side, but again, that's 360 divided by the number of sides, which is 4, so 90. And then for this one, we actually are already given the radius. The radius is already labeled for us, and that is 7. So 7 centimeters. But we need the apothem, which that isn't drawn in. So I'm going to draw in the apothem. And then remember too, so if I were to draw in another radius, it's this entire angle that is 90, and the apothem is bisecting it. So each of these is 45. And then because this is 90, that means this angle down here actually for both is also 45. So you get a 45, 45, 90, which is the other special right triangle that we have. I know that's 7. So I'm going to review that formula with you here. That's not the best triangle. Okay, so for a 45, 45, 90, you have, it's isosceles, so your two legs are the same. And then your hypotenuse is your leg multiplied by the square root of 2. Okay, so if I know that my hypotenuse is 7, because that's my radius, and I need the apothem. So in my formula, I'm just going to call that x for right now. That's what I need to find. So I actually would have to set up an equation. We did this back in chapter 8 when we were working with right triangles specifically. So I'm going to set up the equation that my hypotenuse, which is x times the square root of 2, is equal to 7. Okay, so to solve for x, since these are multiplied, I would have to divide by the square root of 2. So x is equal to 7 divided by the square root of 2. Now this, I am okay with you rounding. The other one, because they were just multiplied together, and I had just left it as the exact, but it's not simplified to leave this in a denominator. So I would be fine with you actually dividing these to get a decimal versus simplifying. So 7 divided by the square root of 2, so it's approximately, I am going to round this to 2 decimal places, 4.95. Okay, so if that's 4.95, then I also know this other side would be 4.95. Oops, 95. And that is half of the length of my square. So each of these would be 4.95 here, meaning a full side of my square would be 4.95 times 2, so approximately 9.9. So to find the perimeter of my polygon, I'd be multiplying 9.9 by the number of sides, which is 4. And that is 39.6 approximately. That would still be centimeters. Okay, so then again, for my area, I'm taking my apothem multiplied by my perimeter and dividing by 2. So my area is 4.95 multiplied by 39.6 divided by 2. And I get 98.01. And that would be centimeters squared. And now because I was rounding the apothem and therefore the perimeter is also rounded, the area is slightly rounded, it isn't exact. But as long as I can see how you're rounding and how you're finding everything, thinking ahead to a test, then you're okay. Okay, so one last one, and again, this one's going to work out differently also. We have a pentagon. So the measure of the central angle, we have 5 sides, so 360 divided by 5, and that is 72. So again, that central angle is from one radius to the next, so the apothem divides that in half. So 72 divided in half is 36. So each of these is 36. So I'm actually going to draw one of those out here. I'm going to kind of rotate it. So my 36 is here. And this is my hypotenuse because that's already labeled. That's 10. So I don't have a special right triangle here. So this is a case where we're going to be using SOHCAHTOA, sine, cosine, or tangent. So I have the radius already. The 10 that's labeled is the radius, so 10 inches. And if I want to find my apothem, that would be this length here, PS. So on the triangle I redrew, I'm just going to label this A. That's my apothem. And that's what I'm going to find first. So reviewing SOHCAHTOA, this is one way that I write it. So just as a review, its sine is opposite over hypotenuse, cosine is adjacent over hypotenuse, and tangent is opposite over adjacent. So our angle right now is 36. The apothem would be the adjacent side, since this over here is the opposite side. The 10 is the hypotenuse. So since I am looking for the adjacent and I have the hypotenuse, my ratio is going to be adjacent over hypotenuse, so I'm going to use cosine. So my equation would be cosine of 36 degrees is equal to my adjacent, which is A, divided by my hypotenuse, which is 10. And then I would solve this equation for A, so I have to multiply both sides by 10. And I am going to round A. So if I type in 10 times cosine of 36, and again, I'll round this to 2 decimal places, so approximately 8.09. So that is my apothem, and that would be in inches. Sorry for the pause. Somebody was at my door while I was recording. Okay, so I have the apothem. Now to find the perimeter, I would need to know this length of the right triangle. I need to know this opposite side. I'm going to call that x for right now. And I'm not going to use my apothem as part of any of my ratios because I just rounded that value. I'm going to use the 10. So I have the opposite that I'm looking for, and I have the hypotenuse. So I have opposite over hypotenuse. I'm using sine. So to find x, I would set that up as sine of 36 should equal the opposite, which is x over the hypotenuse 10. Multiply both sides by 10. So then x will equal, and I can type that in my calculator, 10 times sine of 36. So 5.88 approximately. And the reason I'm rounding to 2 decimal places for these is so that if I round my final area answer, if I wanted to round that to 1 decimal place, it's a little more accurate since I rounded the middle answers to 2. It's still going to be more of an approximation because I'm rounding in the middle, but that's why I'm doing some rounding to 2 decimal places, some rounding to 1. So if this is 5.8, this is also 5.88, and that means a full side length would be 5.88 times 2, so about 11.76. And so my perimeter would be 11.76 multiplied by 5 sides, which is 58.8 approximately. And that would be in inches. And then since I have the apothem and perimeter, I can find the area. So again, apothem times perimeter divided by 2. Divided by 2, and I get 237 points. So now if I round this to 1 decimal place, 237.8. And that would be in inches squared. Okay, so you'll have your practice. Make sure, like I had written down, you have your 30, 60, 90 on the front, your 45, 45, 90 formula from example 3, and then SOHCAHTOA from example 4. So any of the problems could use any of those. You just have to pick out, based on the information you have, what you need to use to find what you still need. So we'll go through the assignment on Monday, and you can let me know then if you have any questions.